For my final project, I decided to explore using a Hill cipher to encrypt images. First, we need to know what a Hill cipher is. A Hill cipher is a block cipher that was created by Lester Hill in 1929. It uses matrix multiplication to encipher and decipher messages. So how does it work? Well, it requires two things: a key and a numeric representation of data in a matrix. A key is simply a square matrix that, in the context of encoding the alphabet, must be invertible mod 26. So for our example, we will use this 2x2 key. The data must be a matrix within rows. When enciphering the alphabet, we assign a number to each letter. So A is 0, B is 1, all the way to Z being 25. So let's say we want to encipher the words "Hello World." Well, first we need to represent it in the form of a matrix. So by writing pairs of letters as column vectors, we can easily convert this to a numeric matrix. Now to encrypt it, we just need to multiply this new matrix by the key. The resulting matrix is the encrypted data, and if we then convert that back to text, we just see the encrypted text. Now, it might be helpful to know what the modulus operator does. It simply returns the remainder. This means that values wrap around. For example, 5 mod 10 is 5 because 5 divided by 10 is 0 with a remainder of 5. But 10 mod 10 is 0 because 10 divided by 10 equals 0 with a remainder of 0. So to decrypt it, we multiply the encrypted matrices by the inverse of the key. If we then write this back out as text, we will get the original message. So how does this apply to images? Well, first we need to know what exactly an image is. Simply put, an image is an n by n matrix of tuples representing red, green, and blue color values. And unlike text, we don't have to transform or rearrange values to apply the Hill cipher, because an image is already a matrix. So the algorithm I'm going to implement in my code works like this. First, we create a key to encode the image with. We then split the image into 3 matrices that are the color channels, red, green, and blue. We then multiply each of the matrices by the key and recombine them to form the encrypted image. To decrypt, we simply extract the key from the key image, we modularly inverse the key, and then we encrypt the encrypted image with the inverse key. So I set off to code it. I decided to use Python because Python has some very convenient libraries that make converting images to matrices very easy. There's also libraries to perform linear algebra calculations like modular inverse and matrix multiplication. So this shouldn't be that hard, but it was that hard. And here's why. My first problem was with generating the key. So I thought, why not just use random numbers? Because, what could go wrong? Well, turns out this can go wrong. But more specifically, this can go wrong. And this clearly says that our matrix is not invertible mod 256. And it was at this moment I learned something. Not all square matrices are invertible mod 256. So I had to think of a solution. So naturally, I coded this. Essentially, while the matrix is not invertible, try again. And eventually, it will be invertible. Cool. Problem solved, right? Nope. And here's why. So let's say we're encrypting this image. This image is 400 pixels high and 600 pixels wide. This means that our key has to be 400 by 400, and that's a problem, because that algorithm I just described works for keys like this, but not for keys like this, or more specifically, keys like this. It's just too big. It takes too much time to randomly generate values that happen to work. So this gave me 2 options. I can either use a better algorithm for generating keys, or my personal favorite, just generate smaller keys. So instead of generating keys like this, I'll generate keys like this. But I can't multiply a small key by a huge image. So instead, I'll multiply that small key by smaller subsections of the image. So this should work, but it didn't. And here's a flowchart to demonstrate what happened. We started with a dog, we encrypted it, and we had something that definitely wasn't a dog, and then we decrypted it, and then had even less of a dog. But why? Well, it turns out JPEG images are compressed. Essentially, If this was our encoded image, after we saved it to a JPEG, this was our encoded image. And if you'll notice, it's almost the same, but not quite. Essentially, when you save something as a JPEG, it compresses it and throws away some of the data. So then when we go to decrypt the image, we're missing the original data, so it doesn't work. So the solution is just don't compress it. So here's an example. Say we want to encrypt this picture of a dog. First, we randomly generate a key. In my program, I used a 3x3 key. And it's important to note that in images, the red, green, and blue values range from 0 to 255. So instead of evaluating everything mod 26, we're evaluating everything mod 256. So this is our randomly generated key that we will encrypt the image with. Now, if we tile this to form an image, this is the image we get. So step 2 is we split the image into its color channels, red, green, and blue. We then multiply each color channel by the key in 3x3 sections. We then combine the color channels to get the final encrypted picture. Now, to decrypt the picture, we split the encrypted picture into its 3 color channels like we did before. We then multiply each color channel by the inverse of the key. And then when we combine those color channels, we get the original image. So in overview, we first start with the image we want to encrypt. We then encrypt it, and the program gives us the encrypted image on top and then the key on the bottom. We then give the program that key and that encrypted image, and it can give us back the original picture.